Suppose you have an interesting sequence of numbers. You can represent it by listing its terms. Maybe it is defined in a recursive way, or maybe you even know the explicit formula for every term. But today I'm going to show you a new way of representing your sequence, one that helps you find closed form formulas, gives rise to new operations on sequences, and much more. Let's take each term of your sequence and multiply it with the power of x, which corresponds to the position of this term in the sequence. Let's also start counting with 0. So, for example, the number 15 has index 4 in this sequence. Since each term comes with its own power of x, we can sum all of them without worrying about messing up our sequence. Let's simplify the expression a bit. And we've now got an infinite power series where our sequence is encoded as coefficients of powers of x. We'll call this the generating function of our sequence. Let's name it a of x. So why would somebody do that? Why complicate our sequence so much? Turns out the generating functions have many uses. Let's see how to use them to find the explicit formula for a sequence given by a recurrence. In our case, the recurrence is valid for all numbers n greater than or equal to 1. So let's sum over this recurrence for valid n, while multiplying with x to the n. It's important to remember that these aren't real power series that we're used to, in the sense that they don't sum to a certain value and we aren't plugging any value for x in our generating function. Try to view them as neat boxes for your sequence, or to borrow from a certain book, a generating function is a clothesline on which we hang a sequence of numbers on display. Regardless, we can manipulate them just as well, so let's change the index and factor out x. We can see that our generating function begins to appear in the equation, so let's substitute it. On the left side, since we are summing from n equals 1, we have to subtract the first term of our generating function. This series on the right is just the geometric series, so certainly we can replace this as well. What we're trying to do here is derive the formula for our generating function, so let's factor out a of x. Now again, why have we done this? It turns out if we manage to express this function as a series, by the definition of generating function, we can read off the coefficient in front of x to the n, and we'll have our formula. We can use any tools for turning functions into series that we want, but in this case we need partial fraction decomposition. This technique could have its own video, but what we are trying to do is, if we have a denominator like this one on the left, we are trying to find two simpler fractions that sum to get their left side. Using some algebra, you can check that we arrive to this answer 1 and minus 1. Now we use the geometric series again to turn our fractions into infinite series. This is it. We've got our generating function. If you remember the definition, it just remains to read off the coefficient, and we have the formula for our sequence that I've shown earlier. Maybe this sequence isn't very interesting, so let's find the general formula for the nth Fibonacci number. We define the Fibonacci sequence as starting with 0 and 1, and the next term comes from summing the previous two terms. This is expressed in the recurrence below. As before, we're going to try and find a nice way to express the generating function of the Fibonacci sequence. By now, maybe you have noticed what happens when we multiply a generating function by x. It turns out our sequence shifts to the right, and this is precisely what we need to express recurrence. Let's do the same thing as before. Sum over all valid n, in this case 2, then shift the index and factor x. Again, we insert a generating function and subtract the missing terms. Our desired function equals x divided by 1 minus x squared. With a particularly tedious application of the partial fractions method, we managed to express this function too as a series, where phi denotes the golden ratio. To get the formula for the nth Fibonacci number, we have to look at what multiplies x to the n here. So, the nth Fibonacci number is equal to 1 over the square root of 5 times golden ratio to the n minus golden ratio to the minus n. In the remainder of the video, I want to show you how to find generating functions for more interesting sequences. We can tell from the geometric series that the function 1 over 1 minus x corresponds to a constant sequence of 1s. And we already know how to shift the sequence right. We can also put a number next to x to get its geometric progression. And we can use -x to get an alternating sequence. If we want to skip a few terms, we put in x to some power. Now let's ask, since this is a function, can we take its derivative? Yes, as it turns out, we derive just how we would do with a regular power series. But what does this mean for our sequence? We know that when you derive a power of x, you multiply with the exponent and reduce it by 1. After that, if we multiply the entire thing by x, what we have done is multiplied each term of our sequence by its position. So, in this way, we can get the generating function of the sequence 0, 1, 2, 3, and so on. And if we repeat, we get the generating function for the square numbers. But the particularly interesting sequences that generating functions are used for are counting sequences. These are just sequences of numbers which count how many of a certain object there exists of a given size. Let's take combinations as an example. Combinations mean the number of ways in which I can choose a certain amount of items from a larger set. Since I have 5 dinosaurs, there are 5 ways to choose my favorite dinosaur. We read this as 5 choose 1 equals 5. 5 things and choose one of them. More commonly, we use the binomial coefficient to denote this number. In how many ways can I then choose 3 dinosaurs? Let's illustrate all the choices with colored balls, since I don't have that many dinosaurs. It turns out there are 10 ways to choose 3 dinosaurs from a group of 5, or 3 of any other item, of course. And if I write down in order the number of combinations of 0 items, 1 item, 2 items, etc., what I have is a counting sequence. For a case of different sized choices from 5 items, we get the sequence 1, 5, 10, 10, 5, 1. And it is symmetric, since choosing some items is the same as choosing which items to not choose. We continue with zeros, since there is no way to choose 6 items if I only have 5. The generating function for this sequence is easy to read off from the binomial theorem, and you probably have already seen the formula for calculating the number of combinations in high school, so we won't dwell on this. Another object we can count are compositions, or the number of ways to split a number into a list of smaller non-zero numbers. For n equals 5, we have the following 16 compositions. Note that order matters here. It's not a coincidence that this is exactly 2 to the 4, as we'll see. Let's start with n ones and try to build a composition from them. For each red box we have 2 choices. Either write a comma to signify we are moving on to a new number, or write a plus to signify that we are adding the left and right numbers. For example, in the first red box we can either put a comma, which leaves the 1 at the beginning, or put a plus, which adds the 2 ones together into a 2. We make the same choice 4 times, so 2 to the 4th. The sequence that counts the number of combinations is therefore this one. And maybe you can already see what its generating function will be. We can also count k compositions. These are only the compositions which have k elements. For example, the number 5 has these 4 2 compositions. Can we get the formula for k compositions? We could do it by a combinatorial argument again, but I want to show you a cool result with generating functions instead. Let's see what happens if we multiply 2 generating functions. If we write them down in series, it is similar to multiplying 2 long polynomials. Let's split up our result by powers of x. We get no x only if we multiply a0 and b0. We get just x if we multiply a0 and b1x, but also a1x and b0, and so on. So let's write down the general rule for multiplication of series, or convolution as it's called. For a given n, we get every combination of indices for a and b which sum up to n. So if f is the generating function for the counting sequence a sub n, and if g is the generating function for the counting sequence b sub n, what sequence does their convolution represent? Does it count anything useful? It turns out that yes. If we have a line of n objects, this counts all the ways that we can split the line into 2 parts and have the left side be counted by an and the right side counted by bn. Put another way, we use generating functions to encode a structure or a property, so the left side has structure f of x and the right side has structure g of x. This may all sound a bit arcane, so let's give an easy example first. Let's count the number of ways we can arrange n balls into a line such that the line starts with either red or blue balls and must end with an even number of green balls. Here are a few legal objects. So we want to express being red or blue with f of x. For each ball we use, we have two choices. Either it is red or it is blue. So there are 2 to the n ways to build a line of balls of length n using red or blue balls. With g of x, we want to express the property of being even. There is one way to build an even line of 0 balls, no way to build an even line with 1 ball, one way to build an even line with 2 balls, as in you can, and so on. So this sequence is the right one. And we've already seen which generating functions represent these two sequences. By multiplying these two generating functions, we'll get the generating function of the counting sequence in the problem. If you want, you can try to work it out with partial fractions, just make sure to first factor the 1 minus x squared term. As promised, let's use this method to find the formula for k compositions. Let's look at an element of some composition. The only restriction it has is that it has to be non-empty, so bigger than 0. The appropriate generating function is then x over 1 minus x. If we look at the next element, we come to the same conclusion. So the generating function for the number of k compositions of n is just this function multiplied by itself k times. You can find that it simplifies to this form, and we again just read out the formula. Let's write down what we just did. Multiply the generating function by itself k times. The meaning is similar to what we had before, except instead of splitting our line of objects into 2, we split it into k parts. If we sum together all the possible k convolutions of f with itself, we get the following sum, which again, using the geometric series, simplifies to 1 over 1 minus f of x. It isn't hard to imagine that this function now corresponds to dividing our line of objects into an arbitrary number of parts. For demonstration, let's derive the generating function for compositions of n, which adjusts the k compositions of n for every possible k. By subtracting the sequences these two functions represent, we see that this approach gives us the same formula as before, at least for n bigger than 0 when it makes sense. Finally, let's touch on function composition, since what we've done now is basically composite a generating function with 1 over 1 minus x. What does it mean to compose two generating functions? Again, we are dividing a line of objects into an arbitrary number of parts. Each part has an inner structure G, while the overarching collection of parts has outer structure F. Let's demonstrate this with the final task for today. Count the number of composition with an even number of odd parts. We want the outer structure, which is the number of parts, to be even. This is something we have already done before. And the inner structure, which is the size of the part, to be odd, which is just the even function shifted right by 1. Composing these functions like so should give us the generating function for our desired sequence. We'll skip over the algebra that brings us here, but we get 1 plus x halves times 1 over 1 minus x squared minus 1 over 1 plus x minus x squared. If this reminds you of the generating function for Fibonacci numbers, you're right. If we work out the power series for these two generating functions and then subtract them, we are left with the generating function for even indexed Fibonacci numbers, plus 1 at the start. Now this is just barely scratching the surface of what generating functions have to offer. But this is more than enough for one video, so thanks for watching and goodbye.